So one thing that we did, and this is work by Bansal et al. From OpenAI, is we said, okay, well, can we demonstrate some unusual results in self-play that would really convince us that there is something there? So what we did here is that we created a small ring, and you have these two humanoid figures, and their goal is just to push each other outside the ring. And they don't know anything about wrestling, they don't know anything about standing or balancing each other, they don't know anything about centers of gravity. All they know is that if you don't do a good job, then your competition is going to do a better job. Now, one of the really attractive things about self-play is that you always have an opponent that's roughly as good as you are. In order to learn, you need to sometimes win and sometimes lose. Like, you can't always win. Sometimes you must fail. Sometimes you must succeed. So let's see what will happen here. Yeah, so the green humanoid was able to block the ball. In a well-balanced self-play environment, the competition is always level. No matter how good you are or how bad you are, you have a competition that makes it exactly the right challenge for you. Oh, and one thing here, so this video shows transfer learning. You take the little wrestling humanoid and you take its friend away and you start applying big, large random forces on it and you see if it can maintain its balance. And the answer turns out to be that yes, it can, because it's been trained against an opponent that pushes it. And so that's why even if it doesn't understand where the pressure force is being applied on it, it's still able to balance itself. So this is one potentially attractive feature of self-play environments, that you could learn a certain broad set of skills, although it's a little hard to control what those skills will be. And so the biggest open question with this research is, how do you learn agents in a self-play environment such that they do whatever they do, but then they are able to solve a battery of tasks that is useful for us, that is explicitly specified externally? Yeah. I also want to highlight one attribute of self-play environments that we've observed in our Dota bot, and that is that we've seen a very rapid increase in the competence of the bot. So over the course of maybe 5 months, we've seen the bot go from playing totally randomly all the way to the world champion. And the reason for that is that once you have a self-play environment, if you put compute into it, you turn it into data. Self-play allows you to turn compute into data. And I think we will see a lot more of that as being an extremely important thing, to be able to turn compute into essentially data or generalization, simply because the speed of neural net processors will increase very dramatically over the next few years. So neural net cycles will be cheap, and it will be important to make use of these newly found overabundance of cycles. Now, I also want to talk a little bit about the end game of the self-play approach. So one thing that we know about the human brain is that it has increased in size fairly rapidly over the past 2 million years. My theory, the reason I think it happened, is because our ancestors got to a point where the thing that's most important for your survival is your standing in the tribe, and less the tiger and the lion. Once the most important thing is how you deal with those other things which have a large brain, then it really helps to have a slightly larger brain. And I think that's what happened. And there exists at least one paper from Science which supports this point of view. So apparently there has been convergent evolution between social apes and social birds, even though in terms of various behaviors, even though the divergence in evolutionary timescale between humans and birds has occurred a very long time ago, and apes and birds have very different brain structure. So I think what should happen if we succeed, if we successfully follow the path of this approach, is that we should create a society of agents which will have language and theory of mind, negotiation, social skills, trade, economy, politics, justice system, All these things should happen inside the multi-agent environment. And there will also be some alignment issue of how do you make sure that the agents we learn behave in a way that we want. Now, I want to make a speculative digression here, which is, I want to make the following observation. If you believe that this kind of society of agents is a plausible place where fully general intelligence will emerge, and if you accept that our experience with the DOTABot, where we've seen a very rapid increase in competence, will carry over once all the details are right. If you assume both of these conditions, then it should follow that we should see a very rapid increase in the competence of our agents as they live in the society of agents. So now that we've talked about a potentially interesting way of increasing the competence and teaching agents social skills and language and a lot of things that actually exist in humans as well, we want to talk a little bit about how you convey goals to agents. And the question of conveying goals to agents is just a technical problem, but it will be important because it is more likely than not that the agents that we will train will eventually be dramatically smarter than us. And this is work by the OpenAI safety team by Paul Cresciano et al. And others. So I'm just going to show you this video, which basically explains how the whole thing works. There is some behavior you're looking for, and you, the human, gets to see pairs of behaviors. And you simply click on the one that looks better. And after a very modest number of clicks, you can get this little simulated leg to do backflips. And there you go. It can now do backflips. And in this, to get this specific behavior, it took about 500 clicks by human annotators. The way it works is that you take so this is a very data efficient reinforcement learning algorithm, but it is efficient in terms of rewards and not in terms of the environment interactions. So what you do here is that you take all the clicks, so you've got here is one behavior which is better than the other. You fit a reward function, a numerical reward function, to those clicks. So you want to fit a reward function which satisfies those clicks, and then you optimize this reward function with reinforcement learning. And it actually works. So this requires 500 bits of information. We've also been able to train lots of Atari games using several thousand bits of information. So in all these cases, you had human annotators or human judges, just like in the previous slide, looking at pairs of trajectories and clicking on the one that they thought was better. And here's an example of an unusual goal where this is a car racing game, but the goal was to ask the agent to train the white car to drive right behind the orange car. So it's a different goal, and it was very straightforward to communicate this goal using this approach. So then, to finish off, alignment is a technical problem. It has to be solved. But of course, the determination of the correct goals we want our AI systems to have will be a very challenging political problem. And on this note, I want to thank you so much for your attention. And I just want to say that there will be a happy hour at Cambridge Brewing Company at 8:45. If you want to chat more about AI and other topics, please come by.
I think that deserves an applause. Thank you very much.
So backpropagation is or neural networks are bio-inspired, but backpropagation doesn't look as though it's what's going on in the brain, because signals in the brain go one direction down the axons, whereas backpropagation requires the errors to be propagated back up the wires. So Can you just talk a little bit about that whole situation where it looks as though the brain is doing something a bit different than our highly successful algorithms? Are algorithms going to be improved once we figure out what the brain is doing, or is the brain really sending signals back even though it's got no obvious way of doing that? What's happening in that area?
So that's a great question. So first of all, I'll say that the true answer is that the honest answer is that I don't know, but I have opinions. And so I'll say two things. Like, first of all, given that, like, if we agree, like, so rather, it is a true fact that backpropagation solves the problem of circuit search. This problem feels like an extremely fundamental problem. And for this reason, I think that it's unlikely to go away. Now, you're also right that the brain doesn't obviously do backpropagation, although there have been multiple proposals of how it could be doing them. For example, there's been work by Tim Lillicrap and others where they've shown that that it's possible to learn a different set of connections that can be used for the backward pass, and that can result in successful learning. Now, the reason this hasn't been like really pushed to the limit by practitioners is because they say, well, I got TF.gradients, I'm just not going to worry about it. But you're right that this is an important issue, and one of two things is going to happen. So my personal opinion is that backpropagation is just going to stay with us till the very end, and we'll actually build fully human level and beyond systems before we understand how the brain does what it does. So that's what I believe, but of course, it is a difference that has to be acknowledged.
Okay, thank you.
Yeah.
Do you think it was a fair matchup for the Dota bot and that person, given the constraints of the system?
So I'd say that the biggest advantage computers have in games like this, one of the big advantages, is that they obviously have a better reaction time. Although in Dota in particular, the number of clicks per second of the top players is fairly small, which is different from StarCraft. So in StarCraft is a very mechanically heavy game because you have a large number of units. And so the top players, they just click all the time. In Dota, every player controls just one hero. And so that greatly reduces the total number of actions they need to make. Now, still precision matters. I think that we'll discover that, but what I think will really happen is that we'll discover that computers have the advantage in any domain. Or rather, every domain. Not yet.
So do you think that the emergent behaviors from the agent were actually kind of directed because the constraints were already kind of in place? So it was kind of forced to discover those? Or do you think that that was actually something quite novel that wow, it actually discovered these on its own? You didn't actually have any bias towards constraining it.
So it's definitely discover new strategies. And I can share an anecdote where our tester, we have a pro which would test the bot, and he played against it for a long time, and the bot would do all kinds of things against the player, the human player, which were effective. Then at some point, that pro decided to play against the better pro, and he decided to imitate one of the things that the bot was doing. And by imitating it, he was able to defeat a better pro. So I think the strategies that he discovers are real, and so it means that there's very real transfer, but I would say, I think what that means is that because the strategies discovered by the bot help the humans, it means that the fundamental gameplay is deeply related.
For a long time now, I've heard that the objective of reinforcement learning is to determine a policy that chooses an action to maximize the expected reward, which is what you said earlier. Would you ever want to look at the standard deviation of possible rewards? Does that even make sense?
Yeah. I think for sure. I think it's really application dependent. One of the reasons to maximize the expected reward is because it's easier to design algorithms for it. So you write down this equation, the formula, you do a little bit of derivation, you get something which amounts to a nice looking algorithm. Now, I think there exist applications where you never want to make mistakes and you want to work on the standard deviation as well. But in practice, it seems that just looking at the expected reward covers a large fraction of the situations you'd like to apply this to.
Okay, thanks.
Yeah.
We talked last week about motivations, and that has a lot to do with the reinforcement. And some of the ideas is that our motivations are actually connection with others and cooperation. And I'm wondering if they're enough. And I understand it's very popular to have the computers play these competitive games. But is there any use in like having an agent self-play collaborative games?
Yeah, I think that's an extremely good question. I think one place from which we can get some inspiration is from the evolution of cooperation. I think cooperation, we cooperate ultimately because it's much better for you, the person, to be cooperative than not. And so I think what should happen, if you have a sufficiently open-ended game, then cooperation will be the winning strategy. And so I think we will get cooperation whether we like it or not.
Hi. You mentioned the complexity of the simulation of friction. I was wondering if you feel that there exist open complexity theoretic problems relevant to AI, or whether it's just a matter of finding good approximations that humans, of the types of problems that humans tend to solve.
Yeah, so complexity theory. Well, at a very basic level, we know that whatever algorithm we're going to run is going to run fairly efficiently on some hardware. So that puts a pretty strict upper bound on the true complexity of the problems we are solving. By definition, we are solving problems which aren't too hard in a complexity theoretic sense. Now, it is also the case that many of the problems, so while the overall thing that we do is not hard from a complexity theoretic sense, and indeed, humans cannot solve NP-complete problems in general, it is true that many of the optimization problems that we pose to our algorithms are intractable in the general case, starting from neural net optimization itself. It is easy to create a family of data sets for a neural network with a very small number of neurons, such that finding the global optimum is NP-complete. And so, how do we avoid it? Well, we just try gradient descent anyway, and somehow it works. But without question, we do not solve problems which are truly intractable. So, I hope this answers the question.
Hello. It seems like an important subproblem on the path towards AGI will be understanding language. And the state of generative language modeling right now is pretty abysmal. What do you think are the most productive research trajectories towards generative language models?
So, I'll first say that you are completely correct that the situation with language is still far from great, although progress has been made, even without any particular innovations beyond models that exist today. Simply scaling up models that exist today on larger data sets is going to go surprisingly far. Not even larger data sets, but larger and deeper models. For example, if you trained a language model with 1,000 layers, and it's the same layer, I think it's going to be a pretty amazing language model. We don't have the cycles for it yet, but I think it will change very soon. Now, I also agree with you that there are some fundamental things missing in our current understanding of deep learning, which prevent us from really solving the problem that we want. So I think one of these problems, one of the things that's missing is that, or that seems patently wrong, is the fact that we train a model, then we stop training the model, and we freeze it. Even though it's the training process where the magic really happens. The magic is, if you think about it, the training process is the true general part of the whole story. Because your TensorFlow code doesn't care which dataset to optimize. It just says, whatever, just give me the dataset. I don't care which problem to solve. I'll solve them all. So the ability to do that feels really special. And I think we are not using it at test time. It's hard to speculate about things for which we don't know the answer, but all I'll say is that simply training bigger, deeper language models will go surprisingly far. scaling up. But also doing things like training at test time and inference at test time, I think will be another important boosts to performance.
Hi, thank you for the talk. So it seems like right now another interesting approach to solving reinforcement learning problems could be to go for the evolutionary routes, using evolutionary strategies. And although they have their caveats, I wanted to know if at OpenAI particularly you're working on something related, and what is your general opinion on them?
So, like at present, I believe that something like evolutionary strategies is not great for reinforcement learning. I think that normal reinforcement learning algorithms, especially with big policies, are better. But I think if you want to evolve a small compact object like a piece of code, for example, I think that would be a place where this would be seriously worth considering. But this, evolving a useful piece of code is a cool idea. It hasn't been done yet, so still a lot of work to be done before we get there.
Hi, thank you so much for coming. My question is, you mentioned what is the right goal is a political problem. So I'm wondering if you can elaborate a bit on that, and then also, what do you think would be the approach for us to maybe get there?
Well, I can't really comment too much because all the thoughts that we now have a few people who are thinking about this full time at OpenAI. I don't have enough of a super strong opinion to say anything too definitive. All I can say at a very high level is, given the size, like if you go into the future, whenever soon or later, whenever it's going to happen, when you build a computer which can do anything better than a human, it will happen because the brain is physical. The impact on society is going to be completely massive and overwhelming. It's very difficult to imagine, even if you try really hard. And I think what it means is that people will care a lot. And that's what I was alluding to, the fact that this will be something that many people will care about strongly. And as the impact increases gradually with self-driving cars, more automation, I think we will see a lot more people care.
Do we need to have a very accurate model of the physical world and simulate that in order to have these agents that can eventually come out into the real world and do something approaching, human level intelligence tasks?
Yeah, that's a very good question. So I think if that were the case, we'd be in trouble. And I'm very certain that it could be avoided. So specifically, the real answer has to be that, look, you learn to problem solve, you learn to negotiate, you learn to persist, you learn lots of different useful life lessons in the simulation. And yes, you learn some physics too. But then you go outside to the real world, and you have to start over to some extent, because many of your deeply held assumptions will be false. And one of the goals, so that's one of the reasons I care so much about never stopping training. You've accumulated your knowledge, now you go into an environment where some of your assumptions are violated, you continue training, you try to connect the new data to your old data. And this is an important requirement from our algorithms, which is already met to some extent, but it will have to be met a lot more, so that you can take the partial knowledge that you've acquired, then go in a new situation, learn some more. Literally the example of you go to school, you learn useful things, then you go to work. It's not for your 4 years of CS in undergrad, is not going to fully prepare you for whatever it is you need to know at work. It will help somewhat. You'll be able to get off the ground, but there will be lots of new things you need to learn. So that's the spirit of it. Think of it as of the school.
One of the things you mentioned pretty early on in your talk is that one of the limitations of this sort of style of reinforcement learning is there's no self-organization. So you have to tell it when it did a good thing or it did a bad thing. And that's actually a problem in neuroscience as well when you're trying to teach a rat to, navigate a maze. You have to artificially tell it what to do. So where do you see moving forward when we already have this problem with teaching, not necessarily learning, but also teaching? So where do you see the research moving forward in that respect? How do you sort of introduce this notion of self-organization?
So I think without question, one really important thing you need to do is to be able to infer the goals and strategies of other agents by observing them. That's a fundamental skill you need to be able to learn, to embed into the agents. So that, for example, you have two agents, one of them is doing something, and the other agent says, well, that's really cool, I want to be able to do that too. And then you go on and do that. And so I'd say that this is a very important component in terms of setting the reward. You see what they do, you infer the reward, and now we have a knob which says, you see what they're doing? Now go and try to do the same thing. So I'd say this is, as far as I know, was one of the important ways in which humans are quite different from other animals in the way which, in the scale and scope in which we copy the behavior of other humans.
Do you mind if I ask a quick follow-up? Or?
Go for it.
So that's kind of obvious how that works in the scope of competition, but what about just sort of arbitrary tasks? Like I'm in a math class with someone and I see someone doing a problem a particular way and I'm like, oh, that's a good strategy, maybe I should try that out. How does that work in a sort of non-competitive environment?
So I think that that's going to be a little bit separate from the competitive environment, but it will have to be somehow either probably baked in, maybe evolved into the system, where if you have other agents doing things, they're generating data which you observe. And the only way to truly make sense of the data that you see is to infer the goal of the agent, their strategy, their belief state. That's important also for communicating with them. If you want to successfully communicate with someone, you have to keep track both of their goal and of their belief state and state of knowledge. So I think you will find that there are many, connections between understanding what other agents are doing, inferring their goals, imitating them, and successfully communicating with them.
All right, let's give Ilya and the happy hour a big hand.